with DSIAC. Welcome all. I'm Ted Wells, the DSIAC Director. Just want to give you a quick snapshot of DSIAC with respect to our origins. Again, 6 legacy IACs were combined back in 2014 into what is now known as the Defense Systems Information Analysis Center. There are 9 technical focus areas we support within the defense systems community. And this particular tomography briefing that you're going to hear about today touches on a number of them in terms of ballistics effects and weapon systems, overall survivability and vulnerability type modeling scenarios, advanced materials in terms of additive manufacturing, and overall reliability, maintainability, quality, supportability, and interoperability, which are 4 of the 9, and it has, those are the primary. This particular briefing does actually touch on some of the others a little bit as well. But we operate as a government-owned, contractor-operated information analysis center. We're one of 3. There is a cybersecurity and the Homeland Defense that also address other technical focus areas. Primary purpose of all the basic center of operation information analysis centers is to generate, collect, analyze, synthesize what we call scientific and technical information on behalf of the greater DoD community. So we're primarily geared towards trying to promote knowledge reuse and prevent redundancy of research or efforts. And our overall goal is to be the preeminent information research partner with the DoD community. How we can help you, again, we're funded year in and year out on a variety of different products and services. We offer up to 4 hours free technical inquiry research and have a broad base of subject matter experts addressing all 9 technical focus areas to address various technical questions. Again, if that particular inquiry involves a greater level of effort, we have a couple different vehicles to actually handle externally funded efforts if the requester is so inclined, and that would be the core analysis task and extended technical inquiry, which I'm not going to go into detail on. We generally are always looking for priority scientific and technical information for upload to what DTIC has as their repository is the Research and Engineering Gateway, and we upload information to there, and that's one of the primary sources, as well as various open source databases that we search in response to technical inquiries. We have various information research projects, which include our Information Analysis Center journal, DSIAC journal. We also have aircraft and survivability journals, as well as are involved in, I don't know if folks are aware, but again, through the DTIC, there is a controlled unclassified information and classified journal now as well out, and our folks are engaged in that out of Fort Belvoir. Various training elements that we provide in the 9 technical focus areas, for which this is a prime example of this webinar. And then we get involved in various promotional elements that are interrelated to the defense systems community. Right now our user registered base is a little over 47,000, and we promote various conferences, events, even calls to industry for proposals. So, as an FYI. And lastly, kind of again, how you can help us out in this overall mission, and that is, informing us of interesting R&D papers, again, in terms of scientific and technical information uploads, and providing that so that we can get that up to the R&D Gateway and make that available to the entire DoD community. As subject matter experts, we're constantly looking for additional subject matter experts that we can be apprised of and network folks accordingly to them if they want more detail beyond what we have ready access to in terms of getting to the details of their questions. Notify us of technology advancements. We're constantly doing horizon scanning on our own of a variety of sources to keep apprised of those priority technologies relative to warfighter capability needs. And in terms of promotion, again, we'll be more than glad to hang off our website any kind of related defense system technology events, training, just general sharing of correspondence. That's hopefully folks on the phone are aware of our news digest, and again, trying to keep general community aware of technology. So that's the quick snapshot overview on DSIAC. I'm going to turn it over to Peitsch with respect to the X-ray Computed Tomography scanning brief. I would just like a little administrative. Here's some shuffling in the background. Please, if you would, put your phone on mute. So make sure we're not picking up any information or audio. The thing of note that may be chiming in on that is if you've got your computer mic open, please mute that as well. If you happen to be chiming in via Skype, that will also provide feedback. All right, I'll turn it over to Ryan.
All right. I'm Ryan Peitsch. I'm a non-destructive test engineer with National Technical Systems. I have about 6 years experience working with industrial CT scanners. So that's the short term for X-ray computed tomography. I'll be referring to that as CT scanning. It should be a familiar term to most people. Then the way this will work, we'll start out with just an overview of kind of what CT scanning is and get everybody up to speed. If you already know what it is, and this should be a refresher, and if you don't, we'll bring you up to speed on kind of the process and how we get the data and the limitations of the technology. And then really the best way to proceed after that is just to get into some of the details. So we'll get into some really specific examples for defense applications and go through and actually look at some scan data, get some commentary on it as well. And so here's the basic process of CT scanning. It's very similar to what happens in a hospital. So if you've ever been to a hospital and had a CT scan, our process is not much different than that. Except we can get higher resolution, we use higher energies, and we expose for a much longer time because 90% of the time, or 99.9% of the time, we aren't scanning a living object. So we aren't worried about dosage. And that's the main reason why a hospital scanner is so quick, is you have to worry about dosage, you get low resolution, and kind of just enough to diagnose what's going on. Whereas on the industrial side of things, we're getting very high resolution, and this allows us to go in and see areas that once were unseen unless you have to physically destruct something or cut something open to see. So this is where this will be a benefit, and you'll see that later on. So how it works is, we acquire a bunch of 2D X-rays, which we call radiographs. And the way this works is there's a sample on a turntable, and we're shooting X-rays through the sample as it rotates 360 degrees. And once we have all these X-rays, once we know what the sample looks like through an X-ray 360 degrees around, we can then use something called a back projection algorithm, and we can reconstruct all those X-rays into a volume model, which is a 3D data set, if you can think about a bunch of tiny cubes put together that represent this data with density. So, in an X-ray, you're getting a 2D visual of what the object looks like, and you're getting a 2D visual of the internals. When you do the CT scan, you then have a 3D. So picture a void or some kind of porosity in a 2D view, you'll know where it's at in an XY location, but once you get that CT scan, then you get that third dimension, and you can start attaching volumes and XYZ locations. So you're essentially just jumping into another dimension, and it's just a collection of X-rays is really the only way to think about it. And then once you get the volumetric data, we'll go into these two avenues, I like to call it here. There's surface data that you can pull out of that, so you can get CAD models, wall thickness, point clouds, STLs, and you can also get into the material analysis and see porosity, fiber orientation, relative densities, and we'll get into all that in these later slides. So just some quick applications of industrial CT scanning. This list is ever growing. It's hard to put it all in one slide, but just to summarize, it's used heavily in research and development. In the early stages of design for any kind of verification or validation of a model, CT scanning is very favorable because in that stage of your research and development, you don't have a lot of samples, so when you have to destructively cut something open that you plan to test, you ruin that sample, or you have to make another one, and that can be a time factor and also a cost factor. So with CT scanning, you can peer into things and look inside and still use that part for further testing. So that's a quick, up front, get a scan before you do anything, and that's a good verification to a model later down the road. Another quick, application is for reverse engineering or prototyping. For the same reason, you would use a ferro arm or some kind of laser scanner to model. You can do the same thing with CT, except you can also get the hidden surfaces, and you can go fully out to a CAD model in the end as well. And then in manufacturing quality control, same thing. If there's hidden surfaces, if you're doing first article testing and things like that, you can go in with the CT scanner and actually measure those surfaces and set up acceptance and fail criteria, and actually start getting into using this as a GD&T metrology tool, which is something we'll get into later as well, where that's kind of on the forefront now of getting into that using CT as a metrology tool. And then lastly, for life cycle management, any kind of failure analysis or obsolete components or parts that you don't have a drawing or a CAD model for, a CT scanner can go in and get all those surfaces, and you can create a full drawing or a full CAD model right from a scan. So here's a quick image of what our CT scanner looks like at our Bell Camp location within NTS. We actually have two systems there, and this is the larger of the two. So just to give you an idea of what we're dealing with. On the left side of that image, you can see there's a source. We have two sources, and then in the middle you'll see the sample on a turntable, and then on the right there's a detector. So what happens is the X-ray beam turns on. Sample will rotate 360 degrees as we project that image onto the detector, and we store all those images. And just to kind of give you an idea of what equipment's out there, the standard right now for industrial CT is microfocus CT, and what that means is you essentially have a small X-ray spot size, small enough to get these resolutions that you see here. We can get down to 2 microns on our 225 kilovolt head, and we can get about 70 and 30 microns on our 450 and 320 kilovolt head. So what that means is the size of those little cubes, that volumetric data set, is going to be 2 microns in any direction. So it's essentially, you can think about it as pixels in an image, and CT scanning would be voxels, is what we would call a 3D pixel. So that's what I refer to resolution. That's what I'm describing. And like I said, we have two systems there. We cover 225 kilovolts up to 450. And right now, there's efforts to go above 450 kilovolts for microfocus. But right now, 450 is pretty much the upper limit, which equates to about 1.5 to 2 inches of steel as a max of material that you can see through with sufficient signal to noise ratio and resolution. And just some quick major programs in CT. We're going to get it heavily into the defense here shortly, but just some other government uses. The NTSB uses this a lot in their failure investigations, specifically the 787 Dreamliner batteries that were catching on fire at the Boston airport back in 2013. They used CT heavily early on to diagnose the issue before they did any tear downs, and we'll see some images of that later on. NASA using it for materials research, and they use a lot of lithium-ion battery technology and qualifying that technology and making sure batteries aren't counterfeit, they're working properly, or if there is a failure, checking that failure ahead of time before tearing anything down, preserving that as-failed state. And then lastly, the Smithsonian is another institution that's using this to digitize their fossil library, which at the end of this, we'll see some images of that as well. So now, the best thing to do is just to get right into the applications, and we can start talking. If you have any questions, I believe we'll go through that at the end, so definitely make note if you see anything that raises a question. So the first application here, I grouped them a little bit by, I guess, the different types of work within the defense industry there. So the first here we're going to start with is ballistics. So for armor plates. What we see here on the left is just a standard hard armor plate with ceramic and then some kind of composite or soft armor backing. And on the right-hand side, you actually see CT images. These are cross-sections that were virtually cross-sectioned from the CT scan data. So within the data set, you can slice, top to bottom, left to right. You can set up custom planes, so you can really go in there, and it's as if you're physically cutting it, except you're doing it all on a computer. So it's a really nice tool, for a non-destructive evaluation. And what we see here is the shot location. You can see the projectile was caught by the backing material, and you can actually see the crack propagation in the ceramic. So right now, this is a huge effort in assessing multi-hit capability on armor plates. So if you shoot a plate in the top right corner, you can actually follow that crack down and see where the worst case scenario would be. So when you do your second shot, you're simulating the worst case scenario. And an X-ray, just a 2D X-ray can accomplish this, but actually a CT scan, if you have the time to get that done in between shots, it definitely helps because you can quantify the volume of voiding and delamination. And another effort we've seen too is identifying the projectile post-shot. You can get the volume of that projectile, what's left over, the shape of the core, and you can also get, the density, the relative densities as well. So if you have some kind of armor plate that has a projectile in it that is unknown, you can pull off these relative densities before you go ahead and pull that out of the plate and ruin anything potentially in there that could have been a tell of what happened. And then lastly, you can get the depth of penetration real easy. You can see from the top down view, you can see that bulge in the backing material. You can do all digital measurements in the software and actually pull that depth of penetration out and get a more accurate reading than you would, on a clay surface or what the traditional ways are. Here's another image. This is a handgun. This is a Beretta M9. So we did a CT scan on this, and you can see one of the slices here on the left, and then a 3D rendering on the right, the transparent view. So this is really useful in testing firearms. If you're going to do cycling, if you're going to cycle thousands of rounds through it, you would want to do a scan ahead of time, several intervals during the test, and then at the end of the test, see if any kind of fatigue, if there's cracking, growing, or the springs wearing down, any kind of mechanical features in there you can highlight, and you'll have an archive of that as you go through the life cycle of the firearm, which is nice. And then any kind of modifications, things like that, if you can go in there and pull surfaces off and add attachments. We've had some grip designs and things like that we've helped out where we scan the gun and you can actually design right off of the scan right into CAD. Here's some ballistics here for ammunition and munitions. Quantifying core volume, core shape, propellant fill, propellant volume. These were all things that you have to physically cut a bullet open to see inside of it to get that information, whereas now we can measure jacket thickness, we can measure incendiary fill, incendiary volume. If you see on the right, you can break out a bullet, all its internals into a CAD model and actually make a digital library of each round so you have a reference point. So if you're doing a lot of range testing, your quality control, this is just another tool you can use to make sure that you don't have any mislabeled ammunition or copycat ammunition. You can actually CT scan it, compare it to the golden CAD model that you have, and you can move forward and be confident that the ammunition that you're testing is as advertised. You can also see a primer there as well. We can virtually unroll that primer and see the propellant fill, which is another nice tool we'll see a little bit of later on as well. Change gears a little bit here into the composites. So in the materials side, this is a truss structure, just a composite truss structure that had a load put on it. And we scanned it before we put a load on it and then after, and this was the post-test. And there was actually a model that goes along with this that predicted when and where those plies were going to start breaking. And we can actually see that in these images. You can actually go in and count those plies and feed that back into your model for validation verification, which, the only other way you could do this without using CT or some kind of ultrasonic testing, you would have to physically cross-section this, and then at which point you could be disrupting the as-failed state is what I like to call it. So this is just a snapshot in time of what it looked like after the test. And you can always go back to the data and look at different areas. So it's a really nice tool for preserving that as-failed state. Here's a few more composite examples using CT scans so we can get void content in the resin. You can actually get a volume of the voiding throughout the entire material and get a percentage voiding. This is very helpful early on in the manufacturing process, and then again as a validation check down the road. And you can also get fiber angle layer by layer, which is a really nice tool. If you have a multi-layer composite with multiple materials in there, you can go layer by layer and actually pull out tensor fields that give you the fiber angle. And you can compare this back to the as-intended design, and again, feed that into a model for failure analysis and just more verification checks for modeling up front. Here's just another quick image, just a more zoomed in view showing some of that porosity that can be quantified in the CT scan. You can plot volumes and XYZ locations of each one of those porosity locations inside of there. And then here's a last slide on just woven composites. You can see in the bottom image on the needle pull-throughs, you can actually see how many plies were damaged on those pull-throughs. So this is a very useful tool in figuring out what collateral damage happened on those needle pull-throughs. And you can see the composite sample on the top left as well. We can virtually section out the outer layer and see inside of it and cross-section even more into that weave structure. Any way we want to, really, we can rotate that around just as a CAD model and strip away different sections, which can be very helpful in confirming a manufacturing process or identifying a defect or a weakness. And then that image on the right is aramid fiber, so you can see any delaminations in there as well. Before and after it gets pressed into a armor mold. And here's a representative example of composites and kind of a different material like a metal or an aluminum and the interfaces and what information you can get from CT scanning there. If you look in here on the bottom right image of this bicycle frame section, you can see the metal and composite interface. There is a voiding on that surface, which when this does get put under a load and get tested, you can predict that's where your failure might occur. So you can have this information ahead of time, which is very useful. In the post-test, you might not know if that was there ahead of time if you didn't have a scan of it or if you had the cross-section. So again, it's just a nice tool to quantify all these features before you go ahead and start your testing. 3D printing, this is an FDM extruded print of a fossil that we actually scanned and sent to the printer. So you can see the internal infill. You can see how the filament's laying, the filament diameter. You can actually quantify all of that on the back end after a scan. So this is a heavily used tool in the field of additive manufacturing right now, specifically for metals. So with the laser sintering devices, if your powder is not getting sintered fully or you're getting voiding or different kinds of defects within your additive manufactured components, the CT scan can actually tell all of that based off density. So if you're getting a lot of metal 3D prints done, it's not a bad idea to get involved with the CT scanning side of things and see, is the print consistent? Is it as intended? Are there overhangs that were intended that didn't quite turn out, but otherwise were hidden inside that you couldn't see unless you either were videotaping the print the entire time or need a CT scan to see in the end. So the big committee right now is the ASTM F42, the Additive Manufacturing ASTM committee. There's a huge push now for using NDE as a CT as an NDE method, one of many methods to qualify and standardize this printing, because as we know, additive manufacturing is starting to become heavily used by almost everybody, including the defense industries. So it's very important to standardize this and come up with ways to prove consistency. We'll switch gears here into electronics. So, lithium-ion batteries, everybody, I'm sure has heard, all the different things that can go wrong. Anytime a lithium-ion battery fails, it's pretty much catastrophic, just the way, if it vents or if there's some kind of puncture, they're just very volatile in that sense. So CT scanning has become almost 100% inspection if you're putting this in a very expensive device or, it's its first time interacting inside of a device where you aren't quite sure the behavior of it. This is a nice tool to, make sure you don't have counterfeit battery cells. That's a huge problem now. You can actually go in and measure tab welds, rupture disc thicknesses, CID devices, Everything inside the CT scan you can measure and quantify and actually trace back to specific manufacturers, which is very helpful in the failure side of things and also upfront making sure you have what was advertised to you as bought from a manufacturer. In that bottom left corner there, you can see that's a cross section of one of those Dreamliner batteries I was mentioning. You can actually slice down from top to bottom and look through all those rolls inside of there and see if there's any foreign debris, any kind of punctures, anything that would lead to, what causes this failure in this battery to catch on fire. Any kind of data you can gather before you start cutting that open physically is where CT would come into play. And here's some more cross sections of batteries. These are pouch cells, so measuring that anode and cathode length in the corners is very crucial in the packaging. The Samsung batteries, everybody knows, those were catching on fire a few years ago, and that was due to the pouch cell here. The corners of the pouch cell were shrunk in, and the anode was rolling over on the cathode and essentially creating a short circuit. So you can check for all that ahead of time, and also if you're putting this in some kind of assembly or some kind of enclosure, you can see all of the forces and stresses that are poking in on those corners or different parts of the battery as well. So that way you're covering and making sure that ahead of time there are no failures that you can see blatantly before you go ahead and test. And then more for electronics here with the circuit boards. It's an invaluable tool for measuring solder fill. You can go in and actually see a cross section, and you can actually quantify, is it 20% full, 80% full. So you can go in, and this is extremely useful in BGAs if you're doing any kind of retooling or you have a large circuit board with a lot of BGA components on there. You can go through and measure the shape of the solder ball, detect any voiding. You can see the head-on pillow defects. There's a lot of tools you can do by cross-sectioning on all these different angles with the CT scan. X-ray can tell you, if you have a void or a misshapen BGA, CT can actually model that for you and actually show you what that looks like in 3 dimensions. And then also with, connectors and what I like to call black boxes. If you have some box of components inside of it and you don't want to open it, you don't have to. You can CT scan it in its pulled out of service state. And you can look inside and you can identify components, and you can even get down and identify counterfeit components based off of exemplar scans of what you know that component to be. So that's very helpful in all kinds of failure analysis, where the very first thing you want to do is get a CT scan to see the as failed state, and then you can go in and start probing and getting more information before you physically open that part up. And then you can see here's a mated connector. So we scanned it in its as mated position, and it had some wire strain pulling it to one direction. And you can actually see several of those pins are actually not mating to the other side of the connector due to that strain. So it's nice to do that sort of in situ testing as well. You can set everything up as it would be tested in the field and scan it in that state and actually interrogate what's going on. And then now we'll get into some of the metrology, and like I said, this is kind of a forefront for CT now, is starting to get this accepted as a metrology tool. So I'll show you some of the examples here. This is an injector, and you can see those tiny chambers and orifices in there. We can measure the diameter and the consistency of the diameter, and you can go in, as you would think, with a CMM using a physical touch probe. We're doing this all with a virtual touch probe, essentially. Using the surface data. So all those internal hidden features that traditional line of sight metrology tools can't get to, CT, it's no problem. It's getting that volumetric data. We can go in and define those surfaces and pull out all those tolerances. And again, for any kind of O-ring or a bezel or a faceplate, something that's very flimsy and hard to use tactile probing or even laser scanning on, you can actually put it in an assembly as it would be used in the field and CT scan it and measure that O-ring compression or that flexibility. That's just very helpful in trying to figure out what's going on inside of a sample without actually having to tear it apart. And you can also pull out the STL and go right to CAD from that as-built part. You don't have to disassemble it yourself. Here's another quick example of 2 rings with another internal component that, again, you'd have to take it apart to scan each piece separately. We were able to scan this as one complete unit and segment out all the different components and preserve the O-ring and then all of the mating features So that way you're getting accurate measurements as it would be tested in the field. And then lastly here to wrap up, just some of the applications, not necessarily defense related, but they're neat images to show for the art and museum world. This is a prayer bead we scanned for the New York Met, and you can actually see how it's half open and it's the size of a quarter, that center picture. That's actually what it looked like. And they were making no attempt to physically open this because it was discovered in the 1500s. So it's very delicate, and they were scared they were going to break it. So we actually CT scanned it and virtually opened it up for them, and that's what these images are showing. This was actually carved out of wood around the 1500s. So you can imagine the amount of detail that went into this, such a long time ago, and being able to use CT to get inside and see these things is really a novel. This is the first time they've ever seen inside of it. They weren't even going to attempt to open it. And then lastly, this is the Smithsonian fossil. So they're digitizing all their fossil libraries, so you can see the difference between rock, fossilized bone. So it's just invaluable. They're not going to chisel away a 20-million-year-old fossil to try and get down to the fossilized bone in there. They're just going to leave it as is. So the CT scanner just gives them another dimension and another tool to see inside of these things. And that's all I have today, and looking forward to any questions anyone has. Again, I'm Ryan Peitsch from NTS Chesapeake, for anyone that joined a little later. I've about 6 years experience with CT scanning. We have 2 CT scanners in our lab, and then, company-wide, we have a bunch of other capabilities as well.
Thanks, Ryan. We do have 2 questions that were submitted. One is, what is the approximate cost of a system like the one you're using?
Okay. Yeah, so the CT systems, so that's a good question because that can vary in cost depending on your application. So there are turnkey systems, and they are cabinet-style systems. So they're just, come on a truck or a flatbed, get delivered and just plug in your generator and do some alignments and you're ready to go. Those systems, really roughly speaking, could be anywhere from $400,000 to $800,000 depending on what you're looking at. And it can even go upwards from there, but roughly I give about that range. That would give you about a 10-inch by 10-inch window or a 12-inch by 12-inch window, and that's what we call a cabinet-style system. If you want to get more into the custom, as you see our big vault system, that's a custom-built system that has 36 by 36-inch window and about 6 feet in height. That's going to be closer to the $1 million, $1.5 million range. Again, roughly speaking, it's all application dependent. A lot of these systems are very custom, so really the sky's the limit as far as what you want. And you can also get much simpler if you're only looking for a few tools out of it. So.
Okay, the second question. How automated is the CT to CAD process in terms of manual segmentation, isosurface extraction?
That's a great question. So the CT scan data goes directly from the scan data. We can go right to an STL or a point cloud. That's the direct export we can do. And the automation of that is 100% dependent on your scan quality. So the longer you scan something and the different types of materials that are in there all influence this. But say if you have a plastic component that's 100% plastic, if you do a nice 1-hour CT scan on that, you can get an auto threshold on that, and you could save out to an STL in less than an hour. And then it's completely automated. The only other side to that is once you have that STL, you would then have to go into another software and start building your step model or another CAD model off of the STL. So we can only get mesh data from the CT scan. It takes more effort and the software to go ahead and get that into a fully editable CAD model essentially.
We'll get a few more coming in here. How long does it take for a radiograph image?
So for just one radiograph, if you're doing a projection, what we typically do, and we do overkill just to get high quality on our scans, we take 3,142 projections as the sample's rotating. And it really depends on what scan quality you want. Typically, we're at about a 1 second exposure per image. So every second, you're getting an X-ray. But you can vary that. You can go down to a quarter of a second or a tenth of a second and get a much quicker scan. You'll have more noise, less resolution, less signal-to-noise ratio. But the time is really up to you. But typically, we're about an hour scan, about 1 second per image.
And then a follow-up to that was, could single images be taken during a laser sintering additive process that would build a volumetric model in situ?
Yeah, so I think there's some research going on in that sense. I think the difficult there is just getting a print system that can it can be housed inside of a CT scanner, because you do have to shield these X-rays inside of a vault or some kind of scanner, and you're also relying on the object to be fairly still during the scan. If it moves, you'll get blurring. So that's a good question, and maybe more of a research topic of how can we integrate X-ray CT into the build process. At this moment, I'm not 100% sure of any turnkey efforts on that. I know there is research going into it, but more or less for the laser sintering process, I think they're just using an optical camera approach, with cameras mounted in there, checking the build as it's going on.
All right, next. Following on towards, to the previous question, can CT be used for inline process monitoring?
Yes, that's another great question. There are some systems that actually are 100% automated, no users needed, where there is inline CT going on, and there's a company, Volume Graphics, that uses software which they call VG Inline, which actually can go ahead and you can pass your part through a CT scanner on the production line, scan it, and get a profile set up and automate the processing as well. For example, if you're maybe say doing circuit boards, and you want to check solder bill after they were scanned. There is already inline X-ray tools, but there's also some inline CT where you can actually scan inline and pull out that solder fill. As long as you know where everything's going to be in space, the processing is just a matter of going through and coming up with a profile and automating that.
Okay, and this specific question actually had an example, such as in tube manufacturing, looking for internal defects, or is the dwell time too long? So do you do it in line?
Yeah, so again, that just is going to be an application question as far as, what are the size of the tubes, what are the size of your defects. You can get away with a 2-minute CT scan, and you can get a lot of information from that. But it's also going to be, is that 2-second scan or is that 5-second scan enough time to actually see inside of the sample and what you need to see. So there's some tricks you can play, and I think in some applications it can work. The higher the resolution, the longer you need to scan. So if you're on that hour to 2-hour CT scan time frame, then probably not a feasible tool to put on the production line. But, down to the 1 or 2 minute acquisition times, it might be a useful tool depending on the application.
Okay, on the lithium battery page, it was noted that stresses could be determined. Could you expand on that comment? For example, are actual stress strains measurable?
Yeah, so the actual stress strains, in a sense, from like a modeling standpoint, I don't think we can pull too much of that from CT. I think where I was going with that is just if you see any signs of fatigue inside of the battery cell, like wear on the electrode, or some kind of discharge that caused arcing or something inside, you can see those types of evidence that got left over. You can model the battery into a surface model and take it to another software and perform stress analysis on that as scanned data set. So if you have a battery that was punctured or something like that, you can actually go in, pull those surfaces out, export that to a external software and perform some stress analysis in that sense. But as far as directly from the CT data, you just have a volumetric data set, so you'd have to pull what you need from that to then move on and do your stress analysis in another software.
And lastly, how do you control the error of the segmentation/quantity or quantify the measurement error?
That's another great question. So that's another tool that, using your scan quality and your scan time, you can put density references in your scans. The more references you use, the better. So if you know what material you're trying to segment, you can have reference materials in there, and you can calibrate your grayscale ahead of time in the reconstruction phase so that you know you're segmenting the proper material. And we've gone into this a few times. One of the best examples is like a rocket motor that experiences charring, and trying to get that virgin material and that char line. That's all a subject. When do you want to define that threshold? It's really up to the user. So having different density standards that say this is a charred material, this is a virgin material, you can then define that number, that ISO value, and you can program that directly into the software. So it would take a lot of, I think, effort up front to make sure you have all of that information, and then you can automate that and post-process that on the backside.
That's all I see is questions, and we're pretty much up against the 12:45 time. Don't hesitate if there are other follow-up questions. You can submit them. Yet, again, worst case to the website access, or don't hesitate to call them and even if you need to, and we'll ensure you get responses back. But appreciate everybody's attendance, and look forward to, we usually do one of these about a month. We'll have another one in the March timeframe. Thanks again, all. Look to have you involved in the next webinar.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.